Welcome to this solution walkthrough for problem number 55, Jump Game. In this session, we'll explore the problem, understand the intuition behind the solution, and dive into the key approaches step by step. Let's get started. The problem is about determining whether you can reach the last index of an array, starting from the first index. The array, called nums, consists of integers where each element represents the maximum number of steps you can jump forward from that position. For instance, if the value at an index is 2, you can jump up to 2 steps forward from that spot. Your task is to return true if it's possible to reach the last index, or false if it's not. The input will be an integer array, and the output is a Boolean value that indicates whether the last index is reachable. Let's look at some examples to understand the problem better. In the first example, the input array is 2, 3, 1, 1, 4. Starting at index 0, where the value is 2, you can jump up to 2 steps forward. You choose to jump to index 1. At index 1, the value is 3, meaning you can jump up to 3 steps forward. From there, you jump directly to index 4, which is the last index, so the output is true. In the second example, the input is 3, 2, 1, 0, 4, and although you can make some progress initially, you'll eventually reach index 3, where the value is 0. This means you can't move forward from that point, leaving the last index unreachable. The output here is false. For further clarification, take a look at the third example where the input is 0. Here, the array consists of only one element. Since you are already at the last index, the output is true. This highlights a special case where no jumping is needed if the array has just one element. These examples illustrate how the problem tests your ability to think through possible paths in the array and determine if reaching the last index is feasible based on the given jump lengths. Now, let's consider the constraints and edge cases. The length of the array can range from 1 to 10,000, and each value in the array can be as large as 100,000. If the array has only one element, the answer is always true because you are already at the last index. On the other hand, if you encounter a 0 in the array and can't jump past it, that will block you from reaching the end. Efficient computation is crucial for large inputs, particularly when the array length approaches 10,000. The problem often requires applying greedy algorithms or dynamic programming to find the farthest reachable index as you iterate through the array. This approach helps you quickly determine if it's possible to avoid getting stuck and ultimately reach the last index. To solve the jump game problem, one of the approaches we could consider is a brute force method using backtracking. The idea here is to explore every possible path starting from index 0 to see if we can eventually reach the last index. At each step, we calculate all the positions that are reachable from the current index based on the value at that index. Then, we recursively explore each of those positions, checking if any path leads to the last index. If we exhaust all possibilities without success, we return false. While this guarantees correctness, the downside is that it involves a lot of redundant calculations, leading to exponential time complexity, 2 to the power of n, and significant space usage due to the recursive stack. This makes it impractical for larger inputs despite its straightforward nature. Another, far more efficient approach is the greedy method. This relies on the key observation that we don't need to explore all possible paths. Instead, we can track the farthest index reachable at any given point. By doing this, we eliminate unnecessary calculations. To implement this, we initialize a variable, farthest, to keep track of the farthest index we can reach. As we iterate through the array, we update farthest using the maximum of its current value and the sum of the current index and its value. If at any point farthest is greater than or equal to the last index, we can immediately return true, as this confirms the game is winnable. If we finish iterating without reaching the last index, we return false. This approach runs in linear time, n, and requires constant space, 1, making it highly efficient. The key takeaway here is that by focusing on the farthest reachable index, we avoid the complexity of exploring all paths. Although the greedy approach is highly efficient, it requires a good understanding of the paradigm and careful handling of edge cases. An alternative is the dynamic programming approach, which provides a more systematic solution. Here, we use a DP array where each entry, dp, I, indicates whether the last index is reachable from index I. Starting with the last index marked as true, we iterate backward through the array. For each index, we check if it can jump to any position where the DP value is true, and if so, we update DP, I, to true. At the end, the value of DP, 0, will tell us if the game is winnable. While this method is more intuitive for some, it is less efficient, with a time complexity of O(n) squared, due to the nested iteration and a space complexity of O(n) for the DP array. While clear and systematic, this approach is better suited for smaller inputs. When comparing the approaches, we see that the greedy method strikes the best balance between simplicity and efficiency. Backtracking, while thorough, is computationally prohibitive due to its exponential time complexity, making it impractical for larger input sizes. Meanwhile, dynamic programming provides a structured way to solve the problem, but its quadratic time complexity makes it less desirable for large arrays compared to the linear time complexity of the greedy approach. By focusing on the farthest reachable index, the greedy solution ensures optimal performance without the need for additional data structures or exhaustive calculations. This makes it the ideal choice for this problem. In summary, the greedy approach offers the best trade-off when solving the jump game problem. It is efficient, scalable, and leverages the critical insight that the farthest reachable index is all that matters. By eliminating unnecessary computations and focusing solely on this key observation, we arrive at a solution that is not only correct but also optimized for real-world constraints. This efficiency and elegance make the greedy approach the preferred strategy for tackling this problem. To solve the jump game problem, we are given an array of non-negative integers, where each element represents the maximum jump length from that position. The task is to determine if it's possible to reach the last index starting from the first index. A straightforward way to approach this is by using a brute force method with backtracking. First, we initialize a recursive function, canReachIndex, which checks if the last index can be reached starting from a given position. The base case for this function is simple: if the current index is greater than or equal to the last index, we return true, as this means we've successfully reached or surpassed the goal. Next, from the current index, we calculate the maximum possible jump and iterate through all potential steps, recursively checking each path for success. For each possible step size from the current position, we make a recursive call to canReachIndex plus step. If any of these recursive calls returns true, we propagate this success upwards by returning true for the current call. However, if none of the steps lead to the last index, we return false, indicating failure to reach the goal from the current path. This recursive exploration ensures that every potential jump combination is considered. To apply the brute force approach, we invoke the recursive function starting at the first index, which is index equals 0. Key insights here include understanding that this approach exhaustively tries all combinations, making its time complexity exponential at O(2 to the power of n). While it's computationally expensive, it effectively demonstrates the recursive nature of the problem. To optimize, we can use techniques like memoization to store results of subproblems or switch to more efficient strategies like greedy algorithms or dynamic programming. Recursion is a natural fit for this problem because the decision at each position, whether to jump further or stop, is inherently recursive. By using memoization as an enhancement, we can avoid recomputing results for the same starting index, reducing the time complexity to O(n) squared. Let's consider a detailed example with the input nums equals 2, 3, 1, 1, 4. We start at index 0, where nums 0 equals 2, meaning the maximum jump length is 2. This gives us two possible jumps, one step to index 1, or two steps to index 2. First, we try jumping one step to index 1. At index 1, nums 1 equals 3, so the maximum jump length is 3. From here, we can jump to indices 2, 3, or 4. Continuing from index 1, we first try jumping one step to index 2. At index 2, nums 2 equals 1, allowing a maximum jump of one step. This leads us to index 3. At index 3, nums 3 equals 1, again allowing only a single step, which takes us to index 4. Finally, at index 4, we've reached the last index. At this point, we return true and propagate the success back through all previous recursive calls. This example highlights the mechanics of the algorithm, exploring all possible jumps, evaluating the base case to check if the last index is reachable, and backtracking to try alternate paths if necessary. Each recursive call either succeeds and propagates true, or fails and explores the next option. The brute force method has significant computational costs. Its time complexity is 2 to the power of n, because it explores every possible jump combination. However, the space complexity is more manageable at n, as it's determined by the depth of the recursion stack. Here's a Python implementation of this approach. We define a helper function, canReach index, that handles the recursive logic. It first checks the base case, whether the current index is at or beyond the last index. If not, it calculates the maximum jump length at the current position and iteratively tries all steps within that range. If any step leads to success, the function returns true. Otherwise, it returns false after exhausting all options. The main function, canReachLastIndex, nums, simply calls this helper starting at index 0. When solving this problem, it's important to account for edge cases. If the array is empty, we immediately return false, as there's no way to jump. For an array with a single element, such as 0, we return true, since we're already at the last index. Arrays with large gaps, like 0, 2, 3, are impossible to complete if the first element is 0, as it blocks progress entirely. Similarly, arrays consisting entirely of zeros, such as 0, 0, 0, will also return false unless it's a single element array. These cases highlight scenarios where the problem constraints or initial conditions make reaching the last index infeasible, and they ensure the algorithm handles all inputs robustly. The provided Python implementation solves the jump game problem, number 55, from LeetCode using a greedy approach. Let's break it down step by step. 1. Variable initialization. The max_reachable variable is initialized to 0. It keeps track of the furthest index that can be reached from the current position. 2. Iterating through the array. The function uses a for loop to iterate through each index I of the input list nums. This loop checks whether the current index is reachable and updates max_reachable based on the jump length at each position. 3. Early termination for unreachable indices. The condition if I max_reachable handles cases where the current index I is beyond the furthest reachable position, max_reachable. If this happens, it means the position cannot be reached, and the function immediately returns false. 4. Updating max reachable index. For each index, max_reachable is updated to the maximum of its current value and I plus nums, I. This ensures that the furthest possible index that can be reached is always maintained. 5. Checking for success. If max_reachable ever reaches or exceeds the last index, i.e., len, nums, 1, the function returns true, indicating that it's possible to reach the last index. 6. Final check. If the loop completes without satisfying the success condition, the function returns false, meaning the last index is not reachable. ### complexity analysis. Time complexity. The function runs in n time, where n is the length of the input list nums. This is because it processes each index exactly once. Space complexity. The function uses 1 additional space, as it only maintains a single integer variable, max_reachable. ### edge cases. If nums has only one element, the function immediately returns true since the starting position is already the last index. If all elements in nums are 0 except the first, it checks whether the first index can directly reach the last. This approach is efficient and handles all cases effectively, making it suitable for competitive programming and production use cases. This is the Java implementation of the jump game problem, LeetCode number 55, which follows the same logic as the Python version. The solution uses a greedy approach to track the furthest reachable index, max reachable, while iterating through the array. It checks if the current index is reachable, updating the maximum reach at each step. If the maximum reach exceeds or equals the target index, the function returns true, otherwise, false. Key differences include Java's type declarations, absence of Python's built-in methods, and the use of math.max instead of Python's max. To solve the jump game problem, let's start with example 1 where nums equals 2, 3, 1, 1, 4. We initialize a variable called max_reachable to 0, which will help us track the farthest index we can reach as we iterate through the array. Beginning at index 0, nums, 0, is 2. Since the current index is within the max_reachable range, we proceed. We calculate the new max_reachable as the greater value between the current max_reachable, which is 0, and the sum of the current index plus nums, 0, which equals 2. This updates max_reachable to 2. At this point, max_reachable is still less than the last index, so we continue. Next, at index 1, nums, 1, is 3. Again, this index is within the max_reachable range, so we proceed. We update max_reachable to the maximum of its current value, which is 2, and the sum of the current index plus nums, 1, which gives 4. Now, max_reachable equals the last index of the array, so we can conclude that it is possible to reach the end, and we return true. Now, let's analyze example 2, where nums equals 3, 2, 1, 0, 4. Just like before, we initialize max_reachable to 0. Starting at index 0, nums, 0, is 3. Since the current index is within max_reachable, we proceed and calculate the new max_reachable as the maximum between 0 and 0 plus 3, resulting in 3. Since max_reachable is less than the last index, we continue. At index 1, nums, 1, is 2. The index is within max_reachable, so we proceed and update max_reachable to the maximum of its current value, 3, and 1 plus 2, which remains 3. Moving to index 2, nums, 2, is 1. Again, this index is within the max_reachable range, so we update max_reachable to the maximum of 3 and 2 plus 1, which is still 3. At index 3, nums, 3, is 0. We proceed as the index is within max_reachable and update max_reachable to the maximum of 3 and 3 plus 0, which stays 3. Finally, at index 4, the current index exceeds max_reachable, which means we cannot reach the end of the array. Therefore, we return false. Lastly, let's consider example 3, where nums equals 0. Here, we initialize max_reachable to 0. Starting at index 0, nums, 0, is 0. Since the current index is within max_reachable, we proceed. We calculate the new max_reachable as the maximum of its current value, which is 0, and 0 plus nums, 0, which also equals 0. At this point, max_reachable is equal to the last index, which is 0. This means we can successfully reach the end of the array, so we return true. The time complexity of this solution is O(n), where n represents the length of the input array. This efficiency is achieved because we use a single for loop that iterates over the array exactly once. Each iteration performs a set of constant time operations. For example, checking if the current index exceeds the maximum reachable position is an O(1) operation, as is updating the maximum reachable index using the formula max_reachable, I plus nums, I. Similarly, checking if we've already reached or surpassed the last index of the array is another O(1) operation. Since these constant time computations happen once per iteration, their total contribution remains linear, or O(n). This ensures that the overall time complexity is determined solely by the single traversal of the array. Now, in some cases, the loop can terminate early if the maximum reachable index already covers or exceeds the last index before completing all iterations. However, this early termination does not affect the worst-case time complexity, which remains O(n). This is because the early exit only reduces the number of iterations in specific scenarios, but in the worst case, the loop still traverses the entire array. Moving to space complexity, this solution is highly efficient, using only O(1) space. We achieve this by relying on a few variables: the loop index, which tracks the current position, and max_reachable, which tracks the furthest index we can reach. Both of these are simple integer variables, needing constant memory regardless of the size of the input array. Importantly, the input array nums is not modified or duplicated, so it does not contribute to additional space usage. Since no additional data structures like arrays or hash maps are used, the final space complexity remains O(1). This simplicity in memory usage makes the algorithm extremely space efficient. To compare, a brute force approach would recursively explore every possible jump path from the first index, attempting all combinations of jumps to see if the end of the array can be reached. This exhaustive search ends up with a time complexity of O(2 to the power of n in the worst case, as each index can lead to multiple recursive calls. In contrast, our greedy approach optimizes this process by maintaining a single variable, max_reachable, which ensures we only consider feasible jumps. This dramatically reduces the time complexity from O(2 to the power of n to O(n), while maintaining optimal space usage. Analyzing further, in the best case, the algorithm terminates early. For instance, if the first element of the array is large enough to jump directly to the end, the loop runs only once, resulting in O(1) time complexity. In the average case, the loop processes most of the array, performing constant time operations at each step, leading to a time complexity of O(n). The worst case occurs when the loop iterates through the entire array without early termination, which still results in an O(n) time complexity. To mathematically prove this, consider that the loop runs at most n iterations, and each iteration involves only O(1) operations. Therefore, the total work remains n multiplied by O(1), which simplifies to O(n). With no additional loops or recursive calls, the overall complexity confirms as O(n). In summary, this greedy approach is significantly more efficient than brute force, reducing the time complexity from exponential O(2 to the power of n to linear O(n), while maintaining an optimal space complexity of O(1). When working on the jump game problem, there are several common mistakes to watch out for. First, overlooking edge cases can be a big issue. For instance, not handling scenarios such as an empty input array or an array with just one element often leads to runtime errors or incorrect results. Many algorithms assume a certain minimum input size or structure, and failing to check for this can cause problems. Another mistake is making incorrect assumptions about reachability. For example, some solutions might assume that every element in the array contributes progress toward the goal without verifying if a position is actually reachable. This can result in infinite loops or wasted computation on paths that can't lead to the solution. Inefficient backtracking is another pitfall. Attempting every possible jump without pruning invalid paths or tracking visited indices can lead to exponential time complexity, making the solution impractical for larger inputs. Finally, ignoring overflow in array indexing is a critical issue. Jumping to invalid indices, such as negative numbers or indices beyond the array size, without bounds checking can cause runtime errors or undefined behavior, especially in languages like C++ where memory safety isn't guaranteed by default. Another common problem is failing to optimize for time complexity. For example, using O(n²) solutions like nested loops instead of a more efficient O(n) greedy approach can make your solution infeasible for large inputs, especially when constraints allow n to go up to 10 to the power of 5. To avoid these pitfalls, it's important to approach the problem with a clear understanding of its constraints. Carefully analyze the input size, potential edge cases, and whether values like negatives or zeros are allowed. Recognizing patterns is also crucial. Many array problems involving jumps or reachability can be solved using a greedy approach or dynamic programming. Identifying these patterns quickly can lead to more efficient solutions. In interviews, it's helpful to start with a brute force approach to demonstrate your thought process. However, you should quickly discuss its inefficiencies and transition to more optimal methods, highlighting how techniques like greedy algorithms or dynamic programming improve performance. It's also important to explain trade-offs clearly during your solution. For example, you might choose a greedy approach over dynamic programming because it's simpler and faster, even if it requires more careful implementation. This demonstrates a deep understanding of the problem and its constraints. Testing edge cases is another essential step. Examples like a single element array, 0, an array like 1, 0, or arrays with all zeros can expose common errors in your logic and make your solution more robust. Beyond the jump game problem itself, similar challenges can help you practice key concepts. For example, jump game 2 requires finding the minimum number of jumps to reach the last index, while longest increasing subsequence teaches optimization strategies through dynamic programming. Minimum cost climbing stairs is another dynamic programming problem that deals with sequential decisions, which can provide valuable practice for tackling problems like jump game. When comparing alternative approaches to solve the jump game problem, each method has its pros and cons. The brute force backtracking approach is easy to implement and understand, but it has exponential time complexity, making it unsuitable for large inputs. Dynamic programming improves this by optimizing overlapping subproblems, reducing the time complexity to O(n²). However, it still uses extra space for memoization and may be slower than greedy methods in certain cases. The greedy approach, on the other hand, is the most efficient, with linear time complexity and minimal space usage. However, it requires careful implementation to ensure correctness, particularly with tricky edge cases. Breadth first search, or BFS, is another interesting option, often used for shortest path problems in unweighted graphs, such as finding the minimum number of jumps. While it's intuitive for certain problems, BFS has higher space complexity due to the queue it requires and may not be the most natural fit for solving array-based problems like jump game. Understanding these trade-offs helps you select the best approach based on the problem's constraints and requirements. Great job working through the jump game problem. We summarized a brute force backtracking approach and highlighted its strengths and limitations. Remember, mastering problem solving involves understanding when to use certain strategies. Thank you for watching, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!